So just a few words about myself. So I'm working for IBM for about 4 years, more on data science, on the software stack for our latest data warehouse appliance, so something physical. But I'm also doing research in theoretical machine learning at Politechnika Poznańska. And when I have a little bit of time, I try to bring both worlds together to try to solve new problems. And today I will talk about data pipeline hyperparameter optimization, which is kind of a crossover between something that we're doing in machine learning. It's really a standard hyperparameter optimization, and something that we're not doing in data science, at least not for the data pipeline, which is the hyperparameter optimization. So my speech will be broken down into 2 parts, maybe. So first I will talk about hyperparameters optimization in general. Is everyone familiar with hyperparameter optimization? Yeah. Okay, so don't worry, because the first part is about the main techniques and the main framework for the state of art in hyperparameter tuning. And the second part will be talking about applying those techniques for data pipeline optimization. And the main empirical results, so if you want to go for lunch earlier, you can, is the fact that if we apply those techniques to our data pipeline operations that all the time have some hyperparameters or some choices that the data scientist has to make, we can greatly improve the accuracy of the final model. In this example, and I will present you a small proof of concept, other results will be published soon, we can increase the accuracy by about 10% for some methods like neural network, which represent a decrease in error by more than 60, 65, 68% if you do the computation. So this is absolutely not something that we should neglect in practice. So before talking specifically about this problem, let's talk a little bit about hyperparameter tuning. So maybe the most example on what hyperparameter tuning is important is gradient descent. So a lot of machine learning algorithm will actually solve an optimization problem using gradient-based descent algorithms, which is an iterative algorithms that will look towards the gradient direction. And this algorithm has one hyperparameter, or several actually, but let's simplify to one, which is the learning rate. And the learning rate will determine how much you will go toward the step of the gradient. And in the best cases, you will converge really fast in few iterations and find your local optimal. So this is the functional G that you would like to optimize. But if you are taking a too small learning rate, then you will still converge, but it will take so much time that maybe in practice it's untractable. I mean, you don't have enough CPU time to do that. And on the contrary, and even worse, if you have too large one, you have a phenomenon called overshooting, and your algorithm will totally diverge. So you will never be able to learn anything and to minimize your function. So there is a trade-off to find, and this trade-off, you cannot learn it directly from the data, but still it is depending on the data. So we will see how we can find this data, this exact value for this parameter. So usually what you're doing is you will pick some random configuration and you will generate a model, learn a new model with this, and you will validate it using your validation process, very often across validation, and you will select at the end the configuration and thus the model that gives you the best metric, in this example, the accuracy. So the state of art in terms of hyperparameter tuning is a framework called Sequential Model-Based Optimization, or SMBO. You can also find it under the name SMAC, Sequential Model-Based Algorithms Configuration. I give one reference that is using this, and it's the most up-to-date, so probably this word will be the new trend instead of SMBO. So for SMBO, what do you need? You need a configuration space over which you will search for your configurations for your parameters. You need a metric to optimize, which is the metric of your model, usually the model accuracy or something a little bit more evolved depending on your problem. You need, the most important part is the surrogate model that you need. So the surrogate model is a kind of approximation of your objective function. So you would like to optimize a functional that is usually really hard to approximate, and it's kind of a black box. So you will build a surrogate that will be much easier to optimize. You also need a criteria to know the next promising configuration. That is to say, well, I know that if I increase slightly my learning rate, I expect better results. So this is this kind of rules and this kind of criteria. And you need a history of information, so all the configuration that you already explored. Which is usually in this basic form the history of score and configuration explored. So let's review really fast few techniques of hyperparameter tuning. So the basic things that you can do is simply use a grid search. So you will have several possible points that represent configuration, and you will simply look for, make an exhaustive search and look over all those points. Of course, this is in practice untractable. If you ever try this, you know that if you have, I don't know, just let's say 10 parameters with 10 different values, it's 10 to the power of 10. If you're trying to optimize a neural network, it's absolutely impossible. Another problem is what tells you that your discretization is good. Maybe your learning rate, the range between too short and too large learning rate will be in between the 2 points that you sample for your grid. So you don't know that. Of course, we have common knowledge. We're sharing papers and configuration, so we can reuse this knowledge, but this is not a sure thing. So here's simply a small example of implementation with scikit-learn. If you're using for prototyping, you can also use it to make hyperparameter tuning really fast. So you define your classifier, here random forest, you define your grid, 3 parameters, value chosen more or less arbitrarily or with my knowledge. And then you simply use a grid search with the cross-validation here, just 10, but you can put stratify sampled or any kind of other techniques. Slightly more evolved techniques consist in looking randomly into your space of configuration. Well, it's slightly better because then you don't have this problem of grid and you can sample your whole space. Still, it's not really intelligent, and you can spend a lot of time just finding the right configuration. And also, once you find a nice configuration, what tells you that you will explore just around and tells you what is the best configuration around? You cannot do that because you're never using any history or any past information. We have slightly more advanced technique using quasi-random sequences, but still it doesn't solve the problem. So to do the implementation with scikit-learn, well, it's exactly the same as for grid search. You simply replace grid search by randomized search cross-validation. So this is another way of doing it really, really fast. If you have a prototyping something with a very small search, grid search, I mean, information space of configuration, sorry, you can simply use random search. Then comes iterated local search. In this case, you will simply use the past points to know in which direction you're looking. So you basically have a neighborhood, and you will look in which direction you would like to go. And you evaluate those configurations, and you select the one that is the most promising or gives you the best iteration. The problem of this is that, of course, you can find local optimum. So you need to have a perturbation process that sometimes will let you go out and transfer you in another part of your configuration or search space. So we have some proofs. It can give you the global optimal, but it can be really, really fast, and that's something that is still really used. So I can recommend one implementation, which is param-ILS. It's in Ruby, not in Python, but it doesn't matter because it's just a wrapper on top of your program. So you can test it by yourself. And the latest techniques, there are some others, but they are not into this framework of SMAC. It's Bayesian approaches, which is kind of the state of art for SMAC optimization. So you have the surrogate model that you want to optimize is this probability, the probability that you will obtain a certain accuracy knowing the hyperparameter configuration. So while you're looking for new parameters and exploring configuration, you will remember your whole history of configuration and score, and you will estimate this probability distribution in order to look for the next point such that it will give you the maximum expected improvement on your accuracy. So there are several types of regression you can do, like Gaussian regressions, like it's the case here, but you have plenty of other techniques depending on your parameters. And there are plenty of implementation, spearmint, robo, hyperopt, biasopt. I'm just giving you an example with hyperopt because this is what I used in practice. So you simply define an objective function that returns you, the cross-validation score, in my case accuracy on the random forest. You define your search space a little bit the same as before for scikit-learn, just the syntax is slightly different, and you can simply start the minimization process. And at the end, you will obtain the best score, the best model, and the best configuration for your algorithm. Okay, so this is the state of art in hyperparameter tuning. This is something that in academia we're doing all the time, but also in practice. We have plenty of it's industry, really it's developed in the industry, as you might probably use them already. But now we will talk specifically about data pipeline optimization, and this is something that I've never seen anywhere. And I was looking, actually it's a problem I faced during my PhD because I needed to collect a huge data set, and I needed to pre-process this data for my algorithms to be able to generate any prediction, any model. And the problem I faced is that I realized that there are so many choices on the way I can pre-process my data, and I have no information whatsoever how I can really get the best out of those data for my algorithms to provide me the best result. So this is why I started to be interested in this. I found a small survey on the internet. It was on Kaggle this year, and the question was, what is the most annoying and the most difficulty that you face at your daily job as a data scientist? And the first answer is dirty data. And I was kind of surprised, but not surprised at the same time. Maybe you would say exactly the same here if you're working on as data scientists. But my question was, if we know that data are so important, why are we really treating it less seriously as the algorithms? We know right now that data are so important, even more than algorithms. We have good understanding on plenty of algorithms. Even neural network, deep learning, we start to understand how they work, what are the capacities, but we know that your algorithms cannot provide you better results than the quality of your data. And my answer at first was like, for this guy to still have a job. And I think it summarized pretty well the job of data scientists right now. It's commonly accepted that most of the time, maybe 70, 80, up to 80% of data scientists' time is spent on pre-processing the data, cleaning the data, handling dirty data. So you might say, okay, so if data scientist is saying like that's my main difficulty at job, it means that it does care about the data. But I'm saying, well, we also do care about our algorithms, but yet we are not tweaking everything in our machine learning process by hand. We're using hyperparameters optimization to find the right parameters and the right combination that gives you the best results. So back to the original question, when I meant what does it mean treating seriously, it means automating things that we do not have to do by ourselves and that a machine can do better than us. And in particular, optimizing data pipeline. So you might be wondering like, okay, but what exactly are you talking about? So I make a small list of questions for you. So when you're dealing with missing values, what are you doing? Discarding? What are you discarding? Rows, columns, imputation. What type of imputation? Are you replacing by the mean, median, model-based? What type of model? What type of hyperparameter for your model? If you have unbalanced data, how are you? Why is that unbalanced? Because you could not sample some classes of your algorithms and of your data distribution, or it's because that's the natural distribution of your data. Are you doing downsampling, oversampling? Or maybe nothing? What bias does it imply? If the data is too large for your computational power, you will use probably dimensional reductions algorithms. What type of algorithms? PCA, but with what kernel? I mean, linear or nonlinear, with what kernel? Are you doing a normalization or not? Are you using subsampling maybe? What technique? What bias does it imply for your data? Outlier detections all the time. What threshold? What deviation measure are you using? Are you using trimming, truncating, censoring, left censoring, right censoring, and the list goes on and goes on. Winsorization, maybe. You have some methods that you would like to use, or some domain requirements. So are you using discretization? What type of grid? What step for your grid? Or maybe clusterization, what method, clustering, sorry, what methods, what hyperparameter for your methods? Maybe categorical encoder. Yeah, but binary, hot one, helmet, backward differences. You have so many choices, and we know that those choices depend on your data, but also on your algorithm. So how can you justify that? And finally, for natural language processing, that's what I will study on this proof of concept. How many tokens are you taking, and what are the size of the m-grams that you're generating and keeping? So there are so many questions, and okay, when you are asking one or two questions, we have general guidelines, but when you start to make a huge data pipeline, this is not that obvious. So usually the process in industry, at least, looks a little bit like this, and it looks like this also in academia, because in academia it's even worse. You skip the data pipeline part before. We just take data sets already pre-processed, mostly pre-processed, and you just apply your methods and say, oh, my algorithm is better, without taking into account the pre-processing impact that it might have. Or you're also hiding your own pre-processing steps. That happens very a lot. So right now it looks like this. You have your raw data, some operations, and you will forward your raw data to the algorithm through this data pipeline. Then you have a meta-optimizer that will suggest some configuration P that you will give to the algorithms that will learn different models, and with your metric you will select the best model and go in production. What I suggest is to do exactly the same thing for data pipeline. You have a meta-optimizer that will suggest some configurations for all your operations in your data pipeline, generate plenty of data pipelines, and with a certain metric, you will select the best data pipeline, and finally forward this data to your algorithms. So, okay, we need a metric. How do you evaluate the best data pipeline? Well, by simply a feedback, a little bit like in a SMAC framework, where we are basing the suggestion for the configuration on the history that we have. And at the end, we want to really optimize the accuracy, right? Or any kind of metric of your model, but not on your data pipeline. It's just a proxy to get the best out of your data. So here's the experiments that I've done. I took 1,000 judgments document from the European Court of Human Rights, so it's like pure text. I removed the conclusions, of course, and I had the ground truth because it was already labeled. The pipeline that I set up was simply a tokenization. It's really classic. Stop word removal, part of speech tagging, lemmatization, and then I generate the n-grams, and finally I do bag of word projection, and this bag of word will be forwarded to different algorithms. So I use decision tree, neural network, random forest, and linear SVM. I define my search space only with 2 parameters, such that it's easy to see, and also very small search space, such that I can do exhaustive search in reasonable time. So you had only the n-grams from 1 to 5, and the tokens in the dictionary for your bag of word projection from 10 to 100,000. So here are the results. So this is the heat map for each of the algorithms, and you can see that depending on the configuration. So here you have, okay, we cannot see, but you can see that on the column you have the number of tokens, and on the line, on the rows, you have the number of n-grams that we kept. This is not surprising that we obtain really bad results for only 10 and 100 tokens, because we know that as data scientists that it's a very bad idea to summarize 1,000 documents in only 10 or 100 dimensions, the most common tokens. But what is a little bit more surprising is that if I plot, first of all, we can see that if we remove these 2 columns that were like kind of the tests, the accuracy really improves in both directions, or really change in both directions, meaning that both operations in your data pipeline really matters. I mean, the hyperparameters in your data pipeline. So here are the best configuration that I found. And it might be a little bit surprising because the best configurations are not when you have the most information, meaning like 100,000 tokens. And also you can have several best configuration. This is not really surprising, but you can see that you can optimize also your time if you take for linear SVM only the tokens, the n grams going until 3 grams, right? And not until 5, because it doesn't improve your results. So here on just the table that that is summarizing the best accuracy that you can have. This is not really important, and I'm running out of time. So this is the first table that I've shown, and you can see that if you fix only in one direction, meaning that you will take the best results when you fix n equals to 1, meaning that basically you are not using any n-grams, you're just using your row tokens, then you can improve your results by adding this operation in your data pipeline by 5.9, 5.4 to 9.8% on your final accuracy of the model, meaning that you have really interest in adding this operator in your data pipeline, so you can really study the influence of each of your operation in data pipeline, and you can optimize it such that you take the best out of it. So now I have a new questions. I was wondering, how much time do I have to spend to find this optimal optimization? Because if I have to spend 35 times more, more times to find the optimal configuration, I'm not really interested, right? So here are the cumulative distribution of the number of configuration you have to explore before finding the optimal configuration. And you can see, for instance, it's not surprising that for random forest and linear SVM it's lower, because we have 3 optimal points and not only 1. But what is interesting is that in the worst case, you will still find your best configuration much faster than with exploring every possible configuration. Okay, here it's not so much. If you take a look at decision tree in your network, you can do it in 31 or 33, and the best, the worst case is 35 configuration that we have. This is due to the fact that the search space is so small that we cannot really evaluate the surrogate model. But I have much better results on large search space, and you can in few configuration obtain something that is really near to the optimal configuration. And also you can give me some bounds. I tell you with 50% probability, how much do you think I need to explore my configuration space and spend time to find the optimal configuration? And the answer is like, well, it's approximately 8 configuration. So I can tell you that you have 50% chance to find in 8 configuration the best configuration. Okay, but I have another question. How can I quantify if an optimal configuration is algorithm specific? Meaning, I would like to transfer my knowledge, something that I learned. What is the optimal configuration for my data pipeline? Is that specific to the algorithm that I'm testing, random forest or linear SVM, or is that specific to my data and data pipeline together? This is really important, because if it's specific to your data pipeline, it means that whatever is the algorithms you will use, you don't have to start this search again and again. You can transfer this knowledge. So for this, I created one procedure that is based on the mean absolute deviation, which measure for a reference point how much the points around are in a given samples are far from it. If you normalize it by the number of dimension in your configuration space, you can actually compare between different configuration space in a let's say not unfair way. So for each optimal configuration that you obtain on your plenty of algorithms, you will build a sample such that you will take one optimal point by algorithms that is the closest from your reference point. You will express everything in a normalized configuration space. Normalized because, as you've seen, I have one axis that is from 1 to 5 and the other from 10 to 10,000, so I still want to account for the first axis. And then I will calculate this NMAD and not NMAP indicator. So the idea, so on the small example that I've shown you, you can see on table 4 the expression of every optimal point in the space, in the normalized space, then you can see also the sample, how they are built. And the idea why we're taking only 1 point per cluster is that per algorithm is that let's assume that you have 2 optimal points in blue for the first algorithms and 3 for the second algorithm. You can see that probably you have a cluster here. So you don't want to take this point into account when you're calculating the dispersion. You want only to account for the closest one, because otherwise it seems a little bit unfair to say that this point is far from this one while it's really, really close. So you have an optimal value that doesn't depend so much on the algorithm. So that's the basic idea. And the results that we obtain. So the idea of doing this test was on a small data set with few points, was simply to be able to observe if this indicator is giving the same results as we would explain and we will interpret as human, right? And this is the case because if you take the first one, you have 0, and this is really, really obvious because if you take this sample, so you can see this point 1 and 0.5 is an optimal point for all my algorithms, meaning that, well, the distance in the sample is 0, and it means that, well, it's kind of universal good point for my data pipeline, at least for this sample of algorithm. But when I take the points in green, then you can see that they still are really close to these blue points that accounts for a lot. So the NMAD indicator is still quite like small, but for the red points you start to see that you have higher value because you start to be further than the other points in optimal points in your configuration space. So the future work, actually work in progress that is done and submitted, is like test on larger configuration spaces where you cannot visualize and you cannot also calculate the optimal value just because they are much bigger. We have some spaces of configuration that are 10 to the power of 100, these kind of things. So of course you cannot look directly for each configuration. And also we would like to optimize the data pipeline generation itself, meaning not only you give me a data pipeline and I give you the optimal configuration for it, but also if you should put or not these operations and trying to build it from scratch, and also to find the right order, because sometimes the preprocessing steps are order dependent. So well, that concludes the talk. So now I guess you're welcome for feeding my idea generator pipeline.
Okay, thank you so much. One short question. Yeah, there's one. Can you switch? Yeah, sure.
Thank you so much. I just wanted to ask if you had certain procedures to, for example, determine if a pipeline configuration that you used is actually better, not just from the point of the score, but if you do any statistical tests on it. I see very often that the traditional parametric tests tend to fail at actually discovering the differences. They tend to be not sensitive enough because the distributions tend not to be normal. And I was wondering what tests do you use, or if does it even matter when you have so much data?
It depends. It depends on the algorithm and on the pipeline. I took on purpose some pipelines and some algorithms. I fixed the seed generation, the grain for the algorithm, and the data pipeline has no randomness whatsoever in it, meaning that it doesn't really matter for this purpose. But I agree that it's something to be studied, because I cannot just say like, okay, I got like I can't remember the figure, but 9.8% improvement in accuracy if you do not fix the seed for your neural network and for the data pipeline. So there is, of course, something to do when you are in production and you actually the variation of accuracy or your metric is not due to the fact that you have another seed and you're really lucky on that, but that is really due to the optimization. But this is already in the SMAC framework, meaning that in Bayesian optimization, I oversimplify the framework, but basically it will assess, it will do a step that is called intensifying, and it will look in an area that looks promising. It will repeat possibly several times the same configuration just to sample this distribution and have an idea how the data or your algorithms behave there. So the idea would be to do the same thing for your data pipeline. Well, yes. Yeah. Yeah, so I guess still it's valid to fix the SIT. You have an idea on that. And yeah, there are more work to do on that for sure.
Okay, thank you so much. Applause, please.